Right, hi everyone. As Malik mentioned, I'm Steve Levine, and I'm here to present some co-work with Professor Brian Williams on concurrent plan recognition and execution for human-robot teams. So intent recognition and robot adaptation are two subproblems that are both necessary to build real robotic systems. So in this picture, we see what's common in very many factories nowadays, especially automobile factories. So huge robots, building things, no people around here. However, it would be great to have a model more like what you see here on the left, where humans and robots can work together as teammates to build things in factories. But in order to do that, again, the robots need to both, one, recognize what their human coworkers are doing, and two, adapt to that accordingly. And there's been a lot of great work in these two areas, intent recognition and robot adaptation. Largely, though, they've been separate research areas. So in this work, we present a unified approach to the problem. Namely, we introduce a single algorithm that concurrently achieves both plan recognition and robot adaptation, one algorithm. And the result is a mixed initiative execution where robots and humans really do work together as a team. So here's a quick example of that. This is a simple domain where we are making breakfast in the morning. So you saw that the human just picked up a coffee mug, and the robot recognized the intent to make coffee and handed the person some coffee beans. However, if the person picks up a glass, the robot knows that you're going to make orange juice instead and not coffee. So that's just a simple example. Another example you may have seen earlier this week in the system demos was when we have a few robots here manufacturing part of an airplane. So what would happen in this example is that the person would pick up a tool and maybe do a few other things, and the robot would recognize what the human needed and hand the proper piece to the person. So the algorithm that we develop is called Pike, and Pike is a plan executive, so it's not really a planner. It's responsible for dispatching activities in a plan as well as making decisions online in that plan. Again, it's a single algorithm that does intent recognition and adaptation. And the choices, the online choices that our algorithm makes are consistent with what the human does in the plan, preconditions and effects in the action, temporal constraints, as well as unanticipated disturbances. And I'll go through each of these in more detail in the rest of my talk. So the high-level takeaway messages I hope I make clear in this are that, firstly, plan recognition and robot adaptation, they really go hand in hand. They're sister problems if you want to have a real robot doing something, and so they should probably be considered together. Secondly, choices and plans are not independent. They're tightly connected through preconditions and effects and temporal constraints. That's going to be the core of my talk. And finally, by analyzing those connections, we can have an executive that can make intelligent choices quickly online. So here's an example of our approach. So this is our plan representation. It's a temporal plan network under uncertainty, otherwise known as a TPNU. And we see it's a fairly rich representation. It's a compact way to encode a number of candidate subplans. So these double circle nodes here represent choices between these different actions. So we can either choose to do this or this. We also have temporal flexibility with simple temporal constraints. So it's a little hard to see the colors here, but these yellowish-looking actions are for the human, and the blue actions are for the robot. So this represents one plan for both the human and the robot. And again, we have different choices for the human and the robot, as well as actions for the human and the robot. So this is a domain for making breakfast. Let's just zoom into the first part of it, which is what you saw in the video, getting a drink for your breakfast. So here, we can have some choices. The human can get a mug or get a glass. The robot can either get some coffee grounds or some juice. And then later, the human's going to either make the coffee or pour the juice. So the first step in this algorithm is that we extract causal links automatically. But these causal links are a little bit different than what is prior in the literature. These causal links are labeled. Namely, they're labeled with choice variables necessary for those causal links to hold. So we call these labeled causal links, and that's one of the key pieces to our approach. So once we extract that, let's consider what might happen online during execution. Suppose that a person, when this is executing, the person picks up the mug, like we did in the video we saw. So when that happens, that means this action that was here, obviously isn't happening, and the causal link associated with that doesn't exist anymore. It's not valid in this instance. So therefore, the system can recognize that this pour juice action, which used to have a causal link, it's no longer justified anymore. So therefore, the human should not be able to execute that action. So we can eliminate that. That's plain recognition right there, because we're recognizing that based on what the person did, picking up a mug, later on the person's going to make coffee. So similarly, we can back-propagate this way again, and the system can recognize that that the robot has to go and pick up coffee grinds for the person. And that's the robot adapting to the human intent. Because if the robot picked up orange juice, the causal links here wouldn't be applicable. All right, so that's a quick example, sort of a toy example about how we can have a single algorithm that propagates and reasons over causal links to actually do plain recognition and robot adaptation. So how does our algorithm Pike fit into a larger architecture? Well, here we have the plan executive sort of sitting at the top. Not shown actually above that is how we actually get the plan. Right now we assume that's given to us as input. Maybe we could make it through a planner, or maybe we could have a person hand-code it, or use a programming language such as RMPL to specify it. And then below Pike, we have three other pieces. We have an activity recognizer. That's what actually watches the human and figures out what choices he or she makes. That could be a computer vision system or any number of sensors. We have a state estimator, which is responsible for estimating the states in the world, and that's useful for detecting disturbances, which I'll talk about a little bit later. And finally, we have an activity dispatcher, which sort of lumps in a lot of lower-level planners like motion planning and other tools necessary to actually act and get the robot to do stuff in the real world. So this is sort of an outline for the rest of the talk. I'm going to start right with the good part, with these labeled causal links, how to extract them and how to use them in a plan. So I'm sure many of you know, excuse me, a causal link represents the notion that some action produces some state, a predicate P, that's consumed or required as a precondition by some later action in that plan. Causal links have been widely used in the literature for partial order planning, for execution monitoring, and they're super useful. However, they're not quite sufficient for these contingent and temporally flexible plans that I just mentioned. And here are a few reasons why. Well, what if A doesn't execute? It's a contingent plan, so we might have chosen another option, and maybe the producer action doesn't run anymore. Or what if the consumer doesn't run? Or and even in these temporally flexible plans, determining the order of events, that the producer occurs before the consumer, is no longer trivial because we don't have precise times assigned to everything. We have flexibility. So in order to overcome these issues, we introduced the notion of labeled causal links, and we have some algorithms that can automatically extract them from our temporally flexible contingent plans. So you might be wondering, what do we label a causal link with? Well, we actually label it with these things called environments. An environment is it's a subset, it's a partial assignment to choice variables in our plan. And intuitively, an environment represents, it's a compact way to represent a whole number of subplans. So let's say we have this environment that makes a choice to two of our variables here. So this actually represents sort of a bunch of different possible subplans, which are sort of slowly being iterated through here, namely all of those subplans that have these two choices in it. You can imagine that an empty environment represents all possible subplans, and a full assignment represents exactly one subplan. All right, so this is just a compact way to encode a bunch of subplans, and this is what we use to label our causal links. Another key thing that I need to introduce before we move on is the notion of subsumption. So we say that one environment subsumes another one, basically if the assignments here are a subset of the second. And what that means intuitively, if we think of the set of possible plans represented by this. This means that the subsuming environment is it represents a smaller space of possible candidate subplans than the subsuming one. The subsumed is smaller than the subsuming. And so that turns out to be quite useful when we actually extract causal links. So here's a very simple plan that I want to show you. We have a simple domain, an action that produces P, at the end of that action, and then another action that requires P, as a precondition. So what would the causal link, or if any, be in this case? Well, it would be this right here. We're going to show causal links with a dotted line, and we label it with the environment of the producer. So basically, this producer will execute in all possible choices. So it doesn't matter if you choose x equals 1 or 2. This will always execute, so we label it with the empty environment here. And so there's the causal link in this case. Maybe you're wondering, why don't we also have one for this equally valid action right here? And the answer is that you could, but it doesn't matter. So this causal link dominates this earlier one, and we can test for dominance by using that notion of subsumption that I introduced earlier. We say that a causal link dominates another one if basically this causal link is guaranteed to occur later in all possible subplans where they both execute. All right? And you can see the paper for more details, but it turns out that extracting a minimal set of dominating causal links is really important for the performance of our algorithm later on. So here's another example, pretty similar to before, except now we sort of switched it around. What are the causal links here? So the answer is that now we do have two, because neither of them are really dominant. So even though this occurs later than this, it might turn out if the executive chooses x equals 2, this wouldn't be a causal link anymore, so it shouldn't really dominate this one. All right? And why is this important? Well, suppose we're executing the plan, and online there's some disturbance that happens. Something goes wrong, maybe right here, and P suddenly gets violated. In that case, our executive can recover from that disturbance by explicitly choosing x equals 1 to reassert P for the later action here. So that's an opportunity to recover. And the final example I want to introduce is a little more complicated. We have a third action here called not P that explicitly, it negates P in our domain. So what are the causal links here? Well, similarly to before, we have these two causal links from the actions, but we also need to extract this threat condition, which we need to generalize to labeled causal links as well. We know that if we choose x equals 2, P definitely won't hold anymore, so we're sort of choosing to violate this causal link, and we need to choose y equals 1 later on if we choose x equals 2. So we can extract this sort of constraint. But all of this only really matters if we choose z equals 1, right? Because if we choose z equals 2, we don't have any requirement that P needs to hold because this action won't execute. So we can also then add this constraint here. So causal links and threats only matter if their preconditions matter. So you may see that we're sort of extracting constraints here, right? So it turns out that our approach basically extracts causal links from the plan and then uses those causal links to encode in a propositional logic, which we show right here. And this basically is what I just described. We also introduce these holds variables that are sort of changed online during execution. So what this basically says is that if we choose z equals 1 and P needs to hold, then either this causal link holds, or we need to choose y equals 1 and this causal link has to hold during execution. So there we go. So that's a little bit about how causal links are used to reason in our plan. There's one key thing I didn't mention, though, is that for a causal link to be a causal link, the producer has to happen before the consumer. So in these temporally flexible plans, I mentioned it's non-trivial to determine that. So we used the labeled all pure shortest path for that. And this is building off some prior work from Conrad in 2009. So the all pure shortest path serves three big purposes. As I mentioned before, it gives you an ordering over events in the plan, which is necessary for causal link extraction, but it also puts the plan in a dispatchable form for online execution, and we can also use it to extract conflicts, temporal conflicts in the plan. All right, so let's just look at this example here. So this is a temporal network, plan network with choice. So we might ask, what is the temporal distance between these two events? So unlike a simple temporal network, it depends on the choice now. It depends on the choice variable. So it turns out that the distance between these two is between 6 and 11 seconds if we go this way. But if we go this way, it's a little less tight, and it's only 2 to 11 seconds. Okay, a few minutes. Okay, thank you. So the key thing here is that we use a notion of this data structure called the labeled value set to sort of compactly store all of this information, basically the shortest path as a function of the choices you make in a table. And we can use that to compute causal links or to compute precedence. Because notice in this example, it doesn't actually matter what choice you make, x equals 1, x equals 2. You can still guarantee that this always happens after this. So finally, I sort of alluded to this earlier. Once we extract causal links, we sort of extract these propositional constraints, and we encode them into a constraint-based knowledge base. What we choose here is what's called an assumption-based truth maintenance system, or ATMS. And an ATMS, you can think of it sort of as a CSP solver that does most of its work offline. And then online, you can sort of query it and ask it questions about some of the assumptions in our plan. So after we extract all of our causal links, we encode them in an ATMS. And that allows our executive to quickly ask online, could I choose x equals 1, given that the human made these choices in the past, and that these causal links were violated? Or could I choose x equals 2, and would the plan still be feasible? So we can quickly ask those questions online. And if for some of you who may be familiar with the graphical notation for ATMSs, this is sort of the notation that we use. You can think of it again as basically we're solving a CSP, but quickly. And finally, once we've done all this great offline work, how do we actually execute the plan? I've alluded to this a lot, but I'll just go through it in a bit more detail. So online, Pike uses this ATMS knowledge base, which again encodes all of these constraints we've extracted. And it continually checks, can I execute this? Can I execute this? It's sort of a greedy approach that was introduced by Conrad in 2009 that checks to see if any event is executable by checking if the conflicts it could extract are feasible. And if they are, it just immediately executes it. So right now, we don't have any notion of a preference or a cost function or different probabilities here. Those are all future work that we want to introduce. We also did some experiments in addition to the robot hardware that we showed you earlier. We generated a bunch of randomly generated TPNUs. Basically, we generated a bunch of random sequential, parallel, and choice substructures and overlaid causal links onto that. So this is actually probably harder than many real-world problems. We found that compilation time, even though there's a large variance, it depends on the number of candidate subplans, sort of linearly. But this value can sort of be exponential in the number of choices, depending on the structure of the plan. And we found that the time online to make choices in the plan was roughly, it was reactive. And I should note that a lot of these times we've actually improved since then by some software refactoring and re-engineering. But generally, Pike can make plans online reactively. So some future work that we hope to do. We'd like to integrate a generative planner at the top level, because one difficulty with this is that if something happens in the plan during execution and there isn't a choice or a contingency to fix that, well, there's not really a lot you can do. So Pike will fail in that case. But if we add some sort of plan repair, that would be great to fix that. Right now, to my knowledge, there aren't any temporally flexible contingent planners. But if any of you know of any, I'd love to hear about them. We'd like to make our approach more probabilistic with execution monitoring and introduce a hybrid domain so we can have some continuous variables and a continuous state space. And let's see, and a few other things like potentially a partially observable state. We assume we can check, if all the causal links hold, which requires knowing the full state of the system. So a partially observable state would be pretty interesting for getting probabilistic guarantees. All right, that's most of my talk. I'll take any questions.
We have time for a couple of questions.
Thanks for the talk.
Thank you.
A question is about controllability issue. You may say something about how to manage, for instance, a controllability problem on this kind of plans, because if you have flexible temporal plan with uncontrollability, in this case from the human operator, even if this kind of plans are rather sequential plan, but in general you should manage this issue. So you can say something about that?
Absolutely. That's a really good question, actually. You know, there's a lot of notions of controllability. There's strong controllability, dynamic controllability, and dynamic controllability in particular seems to me that it's very almost adversarial in a sense. Like you're assuming that the agent or nature will take the worst possible thing for you. We are actually not assuming that here. We're sort of hoping that the human is on your side and it's a mixed initiative execution. So you're both working together towards some goal. So this doesn't really have any dynamic or strong controllability guarantees for the simple reason that if there's an uncontrollable choice at the very end of the plan where the human has to do the final action, you know, if the human does something ridiculous, you know, the plan won't succeed. So.
Sorry, just in any case, my opinion is that you have to manage also the temporal synchronization in this sense. Okay, is not adversarial in this regard, but in any case, you have to manage the temporal flexibility, the temporal uncontrollability, sorry.
Okay.
Okay.
Thank you.
So the form of your plans is such that you have these choice points, and the plans tended to reconverge. So most of the choices tended to be independent of each other.
Right.
Right. So essentially, you're dealing with these small universal plans, if you will, for all the different choices that might happen by the other agent. And my question is, when does this start to break down, right? As the fan out gets bigger and the number of choices or the size of the plan gets bigger.
Right. That's also a very good question. So I should mention that even though these slides that I had did have that fan out and was following a hierarchical structure, internally, actually, Pike does not require that. So you can sort of have this representation where arbitrary constraints can depend on choices that are made. But to answer your question, how does the performance? How does that affect the performance? Well, if you have a lot of choices and a lot of possible different candidate subplans, it does make the algorithm slower linearly in the number of those subplans. So it definitely does have a big performance impact. And so one of the problems with this is that if you have a lot of, if you have a huge number of those, like for many realistic domains to encode all these contingencies, you would need a huge number of those. So that's why it would be cooler to have maybe some sort of planner above this to sort of generate maybe a plan with some flexibility out so far, and then try and execute that without recalling a planner.
Very interesting work. I also have a couple of questions, but we'll discuss that at the break later.
Absolutely.
Thank you. We have to move on. So if you can take the mic. Thanks again for the speaker.